Okay, welcome to this ESSENZ webinar series number. I'm not sure which number it is, but this is dealing with the achievement standard 91193. You have myself, Keith Hartle, and Mari Borthwick. We're co-presenting this, co-hosting, should I say, and we hope we open a few light bulbs, put it that way. So I put it on the screen, you see the title, the official title. I tend to look at it this way, as physics without the numbers. There's a lot that we see and observe, which doesn't necessarily require numeracy to explain it. And hopefully we will develop that idea as we go through. Mari.
We'll run through our Essens Karakia. Ki raro I te korowai kaitiaki o te ketanui a tāne. Mā te hau e pupui te pā kahu kahu ki o mātou waka. Te kaha tāne tangaroa manakitia mai a tātou katoa. I te au o rangi rawa kōpapa. He te oranga o mātou ki pikiaki I o raua Māori. Kia toi mātou I o raua mana. Hui e, tai ki e.
Thank you. So we'll start. There is more than just a Western view to what we see in the world around us. And I just make a reference here to our Maori culture and our toa tama utu tira. I apologize if my pronunciation is not quite there. I have practiced, but still quite. And it talks about the great son of the sun, who captures the whole world as a source of light, warmth, and life. And this was all based on their observations of the environment and the influence the sun placed on the world as they understood it. Hence its place as an atua. And I think we need to take reference to that as we move through our teaching programs, that there is more than one view on which explanation of the world around us. So our plan. We'd like to sort of develop an understanding of what the standard is about, its key principles, some of the contexts, some of the ideas of activities, the assessment, some of the misconceptions. And this will be a bit more evident later on. And then we'll round up with a good night. Moving on, Mari.
Yeah, so let's have a look at the standard. So obviously it's a 4-credit standard, integration of the physics principles in the Earth system. So if we have a look at what the key physics principles are, if you're looking at the explanatory note, what we see is that we're looking at energy sources, so both the sun and terrestrial energy sources. So in particular, that sort of starts to look at the Earth, where the heat energy has come from, both in the past and currently. We look at electromagnetic radiation through transmission, reflection, absorption and scattering, and in particular sort of focusing on long wave radiation, infrared light, and the shortwave radiation from the sun. Again, focusing more around the visible light part of that spectrum. Heat transfer. This is something they're often familiar with from year 11, so radiation, convection and conduction. But the key difference is that when we're looking at all of these things, we are looking through it through the Earth system. So looking at perhaps heat transfer between the atmosphere and the hydrosphere, or between the geosphere and the hydrosphere. So it's looking at those all of these things in terms of the Earth system. So if we go to the next slide, we'll just have a look at what's required at each level. So just like with a lot of the other standards at Achieve level, all we're really wanting students to be able to do is to identify and describe some of those key principles. So they might be required to complete a diagram, complete a table, write some simple descriptions or definitions of terms. But it's that basic understanding. They're able to see some of those key physics principles in play. Moving up to the merit, just as we do with other standards, again, it's around that explanation. They can now actually start to explain how that physics principle is working or is being applied within the context which they have been given. So it's showing a higher level of thinking than is required at Achieved. By the time we get up to excellence, this is where they are really being able to look at a context. They can justify, evaluate. They might be comparing and contrasting things, but they're able to really show really clear links between ideas and between explanations, and in particular, constantly linking it back to the context in which it's been put. So there's some quite nice step ups through there. They're all based around the physics principles. I suppose if we're looking at that, what we see is that the earth science context doesn't really come in until at merit level. So it Achieved, yes, it's within a context, but they're not having to link to it at all at that point. They're just identifying things. We've just added a footnote down at the bottom, and this is something NZQA have been sort of pushing for a number of years, even though they're now going more towards digital exams, which makes this very hard. But annotated diagrams are really, really important. NZQA have always argued that you can actually get an excellence, and we will through a really well annotated diagram, and we've got an example later on in this presentation for you to look at. But you should be encouraging your students to use diagrams where they can, because they are really, really useful, especially for some students who are not so good at writing sentences or paragraphs. They can do a diagram and annotate it to actually get those grades. So I'll pass back to you, Keith.
Thank you. So, working on from those explanatory notes, what are the key physical principles? Well, the sun as a source of energy, the electromagnetic spectrum. I'll get my tongue around it in a minute. The visible spectrum, wavelength, frequency, color, transmission, they're all wrapped up as part of within a key within the idea of a light, visible light. What is visible light? What affects visible light? Now, a lot of this material, in actual fact, is within one of the a learning workbook, whose title is NCA Level 2 Earth and Space Science Learning Workbook. I think it's published by
Used to be
LWL.
ESA, but it's now
Yeah,
Learn Well. Yep.
that's it. Learning Well. Thank you. Forgotten. Yeah. There's a lot of material. Some of the material that is in there is actually outside of the standard. But remember, we're teaching a broad subject here, and the standard reflects part of our teaching program. I mean, that's the best way to put it. I mean, for instance, refraction, dispersion, diffraction is not included in the section on visible light, yet they are valid, yet they are observed. So it is quite likely they will come up within a teaching program. So I would say don't steer away from them. Use it. They're part of the program. But the emphasis comes back to when the assessments come, you focus on the transmission. You focus on the scattering or the reflection or the absorption, whichever component is that question involving it. Moving on, we've also was mentioned, absorption of short and long wavelength radiation by the atmosphere, land, water, transfer of energy. Now, this is one that does bring up some horrible misconception, which we will bring on later on. Density, heat capacity and latent heat. That is a huge concept, which goes a long way to explaining why we have wind, sea breezes, land breezes, and the movement of energy from ocean to atmosphere. Then the Earth is internal heat source, renewable energy, geothermal energy is reliant on this internal heat source, as also are the hot springs. Now, greenhouse effect. Every time we hear the term greenhouse effect, we tend to think about climate change. Now, climate change is not part of the standard, but the greenhouse effect is, because in essence, it is the interaction of long wave radiation and atmospheric gases. The human-induced greenhouse effect has been created by the fact we've been putting some of those extra gases up into the atmosphere. So be wary. Don't hang everything off climate change. That actually comes on later on in level 3 when you talk about atmospheres and the atmospheric unit and also the oceans standard. So some of the common Earth system contexts. Why is the sky blue? Why is the ocean blue? Yes, and people will say it's because the ocean is blue because it's the reflection of the sky. Okay. Why is the sky red at night? Red sky at morning. I mean, that saying, red sky at night and red sky in the morning, goes through many cultures. Bushfires. Now that is extremely topical. If you're actually looking at the news tonight, that's the day of this recording, which is, I think, whatever. They were talking about bushfires in Europe, and there's a huge bushfires running in through France at the moment, as they are through Canada as well. Why are clouds white? Good question. Um, Solar heating, heat transfer to coastal climates. That's our sea breezes. Effect of the albedo on climate, both global and local. That's the melting ice sheet which is a well-documented piece. If you look on some of the NASA, there's a lot of information on that on the NASA sites. The local comparison, and this has been used, I know, in past exams with Central Otago. Why is it so cold in their winters and they're cold winters and yet they're warm summers? And it comes down to the snow on the mountains. Effect of clouds on air temperatures, volcanic action, all of these are legitimate contexts which take back those physical principles. Have you got anything to add to that, Murray?
Uh, Not really. I think you've got I think the key thing, again, just to remind everybody, is that don't focus so much on the climate. You're looking at the effect, like if you're looking at albedo, it's looking at the effect on that heat transfer and how that might change the temperature. So there is a danger to sort of have that overlap with level 3. You might talk about it when you're using it as a context within the classroom, but just be mindful that in terms of exam questions, that the focus of that question will be slightly different.
So thanks. And so, as I mentioned before, there's some thoughts. Real world events are always useful. Look for local contexts. What's around? What are the kids bringing? Even asking them starter questions, because some of them might come up with answers that you really wonder where they're coming from. To be quite honest, I've had this before. Like, I remember being told once that this kid was absolutely totally convinced that the earth was being heated by the molten lava from underneath, not the sun, because the sun was too far away. Totally convinced about that. Took a lot of explaining otherwise, I can assure you. Anyway, and I'm a great believer in using concepts and mind maps to link, making the links, drawing the pictures. Mari?
The other thing I think we can bring in here, and you've sort of alluded to it earlier on, there is a lot of Mataranga Māori. You could be using pūrākau, you could be using whakatauki. So, for example, if you look up about red skies, there's a whakatauki te tātua o te kaha, which literally translates to the belt of te kaha, but it refers to the red clouds that you see at sunset. So it's quite nice to be able often to start any topic that you're looking at within here with anything that you can find that actually relates to the Mataranga Māori as well, and bring in those things so that you can help draw in the Māori perspective. So just, have a search online. There's lots of things there. It doesn't take you, put in a like I just put in red sunset and came up with that whakatauki. It's quite easy to find things if you've already made contact with your local iwi. You could ask them about things that they will have. Lots of local iwi may have their own whakatauki that relate to particular things. There's definitely a lot out there around clouds. So you're looking for those little links where you can bring in that Indigenous perspective to your teaching.
Thanks. Practical activities. I mean, one of the big things about science is actually involving kids in looking at something and actually and being able to make interpretations and being able to learn how to explain what they are observing in the classroom, laboratory, wherever. Simple one with a visible spectrum is just playing with a prism. Uh, and I mean, for some of the kids, they may have done that at year 9, but they're now year 12. Can they remember the exact order in which the white light, the visible light is split up into its component parts? Now we're introducing the ideas of wavelength and frequency to go in with that. So playing with prisms is a way to start this. Scattering. There's a very simple activity using a bit of milk in water and just shining a torch light through it. And you can actually put that analogy to looking at sunlight through a haze or through thin cloud. Radiation experiments with heat lamps, thermometers, color, looking at different colors, the way in which radiated heat is affected by colored cans. I've done it with colored cans and shiny black, white, orange. The kids came up with all sorts of colors. We had spray paint going everywhere. Um, Convection. Tea bag in the bottom of a cup, a transparent cup, of course. I'm just watching the pattern. And a conduction in solids. Try a wooden spoon and a metal teaspoon in hot water. It soon gets that message across. Heat capacity of water. Simple one I've done. This is actually trying to heating equivalent amounts of water and cooking oil over same overheat. Electric heat is preferably set at the same level, so you know that the amount of heat going in is constant. And watching the temperature wise and trying to explain why the oil temperature increases a lot faster than the water. And it's actually a very good one. This is a side issue, of course, to explain why water scalds are so, I suppose, vicious in the way in which that burns or damages the skin. CO2 and heating effect. I've done this with clear plastic bottles. And in one bottle, you've got carbon dioxide, and the other bottle is just normal air sealed at the top. And it's a great way of example of greenhouse effect. And these are all on the net somewhere. I'll- Um, and then also, I've also looked at satellite imagery analysis, particularly for things like carbon dioxide. Um, Now, where was it? I found somewhere, some obscure place, a carbon dioxide map after a volcano eruption, and it showed a whole area where the actual because carbon volcanoes release a huge amount of carbon dioxide or can do, and this was an imagery analysis of it.
I'll jump in. Oh, sorry, if you jump back there for a second. One,
Yeah.
just going back to your convection of fluids, one of my favourite ones to do is get two gas jars.
Mm.
Um,
Yes.
yeah, still using the food colouring idea. So one gas jar, you have your hot water with food colouring in, and your other one just with cold water. You have a piece of laminated card, which you put on top of one, flip over your gas jar, put it on the top, and then you can start with your cold water on the bottom and put your hot water on the top, and you're getting to predict beforehand what's going to happen. And then you do the opposite and they watch what happens. But it's a really nice one because they're always worried that you're going to, as you're pulling the laminated card out from between the two gas jars, that you're going to end up with it everywhere. So it's a bit of a fun one to do. But it's also a very nice one visually for them to be able to see convection working in.
Yeah. Another one I've just thought of too is not on there is density. Um, I've done density experiments with cans of Coke, zero Coke and ordinary Coke.
Yeah, that's a good
You
one.
put one in, you put them in two separate fish tanks, and you'll find one of them sinks and the other one floats. And and they've both got exactly the same amount of liquid inside each can. So what's the reason? And it comes back to density. Now, density is actually very important when you're trying to explain convection. So that's another one. So that one fell off. I've just
Yeah,
remembered it.
that's a really nice one, that one, because they have
Yeah.
to try and work out why it's got different density too.
Yeah. Then they drink the Coke afterwards. Right. On the internet, there are some really, as I hinted before, there's some simulations, there's some imagery, there's also some very good um, simulations from in the UCAR site. I think it's called FET, where they show the greenhouse effect, and it actually shows the interaction of the outgoing radiation with the carbon dioxide and the effect of the changing concentration of carbon dioxide on atmospheric temperature. NOAA and NASA still have visualization tools up there, but please be careful because some of them are doomed. Um, they may they may only be up there for a period of time and then they they might be taken off. We don't know what's happening there at the moment. Um, I don't know how many schools have used Windy. That's a great one for showing wind and ocean data.
It is.
Science Learning Hub has some great resources, and also just get people to talk about local climate, the climate in your area, and why is it different to the climate in other areas. Look for data, and I know that there are various sites which have got, particularly tourist data, has average temperatures for the year, both of ocean and land, and it's always useful to use.
You'll
Any,
also find, I mean, we talked a little bit, I think earlier, Keith, we talked about the
Mm.
fact that have a look on your phones. There's lots of little apps that you can pull up on your phones, like infrared detectors.
Yeah,
Um, so, if you're looking for something, you may well be able to find a phone app that will do exactly what you're wanting to do.
yeah. It's an amazing amount of stuff out there. I didn't really have time to go from find it all, to be quite honest. Right, we'll move on. Mari, I'll let you lead on this one.
Okay, so something that's really important, and I don't know how many people actually do use them, but every year the examiners put together a report based on the performance of students within NCEA. Um, it's got a huge amount of information in it. It'll talk about what students are doing well as areas where there are misconceptions, areas where students could improve. It gives little ideas on things that students have done that have helped them achieve the higher grades. So really what you're wanting to be doing is pulling these out every year. They're available on the NZQA website if you go into the subject areas. Pull these out and actually have a look at them. Probably they're usually available, I think it's by about early February. And so have a look at those. It gives you an idea of how obviously the previous year was marked, but it also will give you some clues perhaps for what examiners might be looking for that following year. Because, you know, if students are consistently doing something wrong, then there's a good chance that if they're giving you advice on things that need to be improved, that might be something that they might be looking for in the upcoming exams. So we'll have a look. Keith, I'll get you to flick onto that,
Yep.
what they actually look like. So what we've got there on the right-hand side in white is part of what the examiner's report looks like. And then on the left there, we've got a question which was for that particular exam. So you can see the question that was there. But what you'll see, so they tell you what typically a student who was being awarded achieved was able to do. So what you can actually do, if you're comparing it with the question itself, you can sort of see the parts that they were able to do. So these students were able to describe the visible spectrum. So if we look at part A, they were asked to describe the spectrum in terms of wavelength, frequency, and colour. So they would have, talked about either end of the spectrum, what colour they were, what frequency they were, what wavelength they were. If we look at that second point, reasons for the colour of the sky during the middle of the day and the evening, which relates to I think it's the question right at the, oh no, it's the second question there. Explain in detail the possible behaviour of visible light as it travels through the atmosphere during the middle of the day. So what you can see is that where those achieve points are, where students were doing that. What they then do is they tell you what candidates who not achieved were commonly doing. So this one's actually quite interesting because it tends to give you the possible misconceptions or ideas that students are picking up, and they're really important to have a look at, because then that's going to help you work out what you want to be aware of when you are teaching, because these are things students will often do. They'll pick up on something incorrectly, and that's what you're really wanting to try and avoid as you're going through with your teaching. And it obviously tells you what students with merit and excellence do. The overall summary that's provided really talks about, like I said, the key strengths and areas of concern where there's a common pattern coming up with students doing things. Quite often, if you have a look at some of these standards, what repeatedly comes up every year is that students are not attempting all of the questions. They might also, if they were doing, for example, question 1, only attempt part A rather than part B and C. So these are patterns that are consistent, and these are what often prevent students from passing. But the only way you're going to be aware of these things is by looking at the examiner's reports. So I really strongly encourage you to pull these down and have a look at them each year and look for the patterns that are coming through to help you with your teaching. Pass back to you, Keith.
Thank you. We mentioned beforehand about the value of an annotated diagram. And this is one that I pulled off one of the exemplars. The question above is explain the possible behavior of visible light as it travels through the atmosphere in the middle of the day, which we were talking about before. And as you can see that this candidate has really provided a lot of information just by annotating a diagram. In some cases, you could actually almost you could get yourself onto a merit status with by annota a good annotated diagram, I believe. There's not everything is perfect. Life never is. But they've done a very they've done a really good attempt at actually providing a very good graphic explanation. And this particular candidate, if I can just move on, I'd say have a good study at that. Have a really good look at it. Get the kids to have a really good look at it. A good and put that annotated diagram up and ask the kids to say, well, what is it explaining? What does it mean to you? But from the same student candidate, they supplemented their annotated diagram with that response. And I've highlighted some of the key points that they've pulled up. So they've actually compared the cloud types with the incoming radiation behavior. They've linked wavelength behavior to scattering. Sorry, what? Yeah, I've worded that rather poorly, but basically, yes. So they've actually not only provided a very good annotated diagram, but they've also provided a very good commentary.
Mm. That's a very good answer.
Yeah. So you can tell where that one's come from, which level that's come from. And I'll have these two. Same question. The response on the diagrammatic response on the left actually shows they have got some understanding. It's not very well annotated, but there is some understanding there. And the other the other response is it's got some points that are right, some points that are not correct. However, that they are beginning to develop an explanation within the context of the question. So the one on the diagram was actually leading, I believe, to an achieved, and the written explanation is leading towards a merit response. So I'm leaving an open door with there are options in ways of answering the question, but often careful planning with an annotated diagram can lead a long way. So, misconceptions. These are some of the great ones that appear on for a variety of different reasons in the not achieved category that I've gleaned off past examiners' reports. It's warmer at the equator because it's closer to the sun. I reckon if you asked 100 people that question a question, why is it warmer at the equator? I reckon 75% of them would give you that answer. It is slightly closer, but it's about 0.008% or something closer to the sun than it is at the poles. It's all to do with the Earth's curvature. I won't go into that. I mean, we could spend another hour talking about that. But that list there of some of the misconceptions, they're just some of the common ones, I believe, that appear in various exams responses. The interesting one down the bottom, fission and fusion, talking about the generation of heat in Earth's core is fission. The sun is fusion. It is often reversed. I have put down the bottom of this slide, there is a link, which there are two PowerPoints which go through some of those misconceptions, and it's important that it is worth looking through those two PowerPoints. I'll also actually point out too, this one about greenhouse gases are an insulating blanket around the Earth. Yeah, that's really quite interesting. They're not an insulating blanket. that seems to be something which I think the media have helped influence a lot of people's understanding that, they act like a blanket
It's a
when in actual,
common analogy, isn't it, that you
yeah,
always hear? Yeah.
yeah. And because you keep on hearing the same thing all the time, it gets ingrained, for want of a better word. Uh, so moving on, we put together a summaries. Now, the question title for this is from 2018 to 2024. What we've done is on the left-hand side is the title of the question, which actually alludes to the uh, context. And on the right, we've just put in some of the major points that the question is actually aiming at. It's not totally encompassing for each question by any means, but it's actually, I hope, will give people a lead into what that question is actually looking at. So if you're looking through past papers, they're your lead. It's your lead to what the question is really talking about. So we did this for 218 through to 224. And I think you might be able to, if you look very closely at it and start reading into it, you can start seeing trends appearing. Right. Well, if there's any questions, somehow I think what we'll do is we'll put up on there an email link, and anything they can put through, any questions can come through to regional representatives or people on the website. Um, and by all means, feel free to ask because if that person doesn't know, they'll pass it on to somebody who does. So you'll get a reply, no problem.
We were going to ask you to rank your confidence levels and about takeaways. Um, we do hope that you have found this webinar a nice introduction if it's the first time that you're looking at this standard, or it's helped sort of solidify maybe your thoughts around what is involved in the standard. I actually personally think it's a really, really interesting one. It's really nice to see physics being taught conceptually, using examples really that students are familiar with and which they're often really interested in. As Keith said, often you've got some common misconceptions around, things like why the ocean is blue. So it's really nice for students to be able to unpack it and really fully understand it. But there's just so many cool things. I mean, what we want to do is get kids looking at things differently. You see so many different visible I'm just trying to think of the right word, but visual effects in the sky. Often, I've been out in the middle of summer and you'll sort of look up and you'll see, part rainbows in the sky and things like that. And that's what we want students to be going away from this course, is that they see something like that and they're starting to use what they've learned to help them actually start to understand what they are observing. And I think Keith alluded to that before, that a lot of this is all around observations and making inferences based on what they've learned. So that's what's really wonderful about Earth and space science, is that it is contextual.
I believe
Um,
I believe, Murray, there's quite a good one running up tonight, which is a halo around the moon.
oh yes, yeah, those sorts of things are just
Yeah.
awesome. And kids will see those, and they're the sorts of questions that they're going to come in. And I mean, you could start your topic quite easily by having a whole lot of photos of all sorts of different things that they may have observed, just to create interest and find out what prior knowledge they actually have. But this is a lovely standard. It's a shame it's not taught more, but yeah, really lovely standard. So we'll flick on. I think, Keith, what have we got? So, as Keith has said before, if there's anything else that you would really like to see from our group that would help you and you're teaching in terms of earth and space science, please don't hesitate to make contact. There is contact details on the website. People are checking those regularly, and we do take careful notice of what our membership are wanting. So please feel free to do that at any time, because we're here to help you and encourage you in your teaching. So I think at this point we'll come to a close. We'll just finish with a karakia. Kia horo te marino, kia whakapapa po namu te moana. He huarahi mā tātou i te rangi nei. Araha atu, araha mai, tātou i a tātou katoa. Hui e, tai ki e. Thank you very much, Keith.
Thank
And,
you. Thank you,
and
Murray, and thank you, everyone else.
kia kite.
Thank you.
Oops. No. Lost the. Hang on, cancel.